Hi everyone, welcome to my channel, and I'm so glad that you clicked on this video. Let me do a quick introduction. So hi, my name is Quentin, and I am an astrophysics student at the University of North Texas in Denton, Texas. I am just but a freshman, and I am loving actually being in school right now. Now obviously I'm not the best student in the world, and nor do I claim to know everything, nor do I claim to be an expert, but I wanted to make this channel because I wanted to start making physics content as soon as I could. And the university has great resources for me to make videos, so I wanted to go ahead and start as soon as I could. So yes, disclaimer, I am a freshman, I'm not an expert at all. I just feel as though since I just started learning these topics, I'm in a good position to explain them in a way that is very digestible, because most of the stuff I didn't know like 4 months ago, and so I'm thinking like, what's a better way to practice what I've learned than try teaching it to others? So that is what we're going to be doing today. So without further ado, vectors. Alright, so what is a vector? Now, that is a good question. Vectors are an extremely fundamental part of physics, and the reason why you learn physics in your first semester of physics is, or the reason why you learn vectors in your first semester of physics is because you're going to be using them all the time for calculations, for coding, for pretty much everything. Anything you can think of, every equation you have is going to have like a vector in it. Pretty much every question you have, like pretty much every question is going to have a question revolving a vector, or like a gravitational field or some sort of force or something. And so it's really important to learn what a vector is, what a vector isn't, and how important they are. So in this video, I hope to give some sort of understanding of that. So, okay, so the first thing you want to know about a vector is what separates it from a scalar quantity. Okay, so what do I mean by that? So if you have a vector, this vector is going to have, it's going to have a magnitude and a direction. What do I mean by that? Excuse my left-handedness. So a vector has the magnitude, so let's say you're going 80 kilometers per hour. It would also say you're going a direction. So let's say left in this example, that would be a vector because you're going in a direction. But if you were to get rid of this direction, then you don't have a vector anymore. This is a scalar. It's a speed. But when you added that vector to it, making it go left, then you added the direction, and it became a vector. And so that is the main difference between scalars and vectors, is that the scalar lacks a direction. Okay. So something else important about a vector is that they are denoted a certain way. So a vector is going to have, it's going to have this little line above it. And I put a V there because we often talk about vectors using velocity, because velocity is a vector because you have the speed and the direction, 80 kilometers per hour, right or left or something. Whereas speed, you know. Let's give a few more examples. So mass. An object like an apple, if it's existing, like just existing, then it has like mass on its own. And then when it gets closer to a gravitational field, like which is near like a planet or something, then it will have weight, because then, because of the big planet, it's going to want to go towards the planet due to the gravitational field, and so then you get the weight of the object. Not to be confused with the mass. So like, for example, if this object, like this apple, let's say it was 0.2 kilograms. That's its mass. And then, if you were to bring it close to the Earth, it would start falling due to the gravitational field. But like, it wouldn't have weight until it gets near an object, and then it would be like pulled towards the object in that direction. In that direction, the downward force that we experience when we're on Earth is the weight, and that's a vector, because that's actually like the planet pulling you down towards the Earth, not just you weighing something because you are made of stuff. You know what I mean? So that's the difference between mass and weight, is the weight is what happens when you're actually near a gravitational field. Okay, two more examples of scalars. So you got time. Time is scalar because you can't go back in time, and it's only in one direction. And so because of that, you can't really give a direction of time, besides it's only one direction. So if you say 3 seconds, then it's like, oh, you went 3 seconds in the future. And you can't really say, oh, I went 3 seconds diagonally or perpendicularly or at a 60-degree angle I went through. No, you can't say that. So for that reason, it's a scalar. Okay, another example of a vector would be friction. So let's say that you have an apple, or no, a block going down a ramp, like so. Now, if this block is going down the ramp, and let's say the ramp is made out of like sandpaper, this block is going to have a force that's pushing it in the opposite direction of its movement. And that is called a friction force, which should be denoted as F, with the little line like so for all the vectors. And that would be the friction force. And so that's a vector because you see this arrow? It's like pointing in a direction. And so since it is, it means that it's a vector because it has a direction. And so those are some examples of vectors and directions and what separates them. And then we'll give another scalar, so volume. Let's say you have like a graduated cylinder and you filled it up all the way. Oh, this kind of looks like a bomb. Just pretend it's a graduated cylinder, y'all. And you fill it up with water. It's not a bomb, I swear to God. Let's say you had 3 liters of water in there. It wouldn't be a vector because you can't like have negative volume. In general, if you can't have like a negative of something, then it's usually a scalar, like displacement. It's just saying, oh, this is how far you went, but it's not saying, oh, this is how far you went in this direction. So it's like not actually a vector. But yeah, that's like another example. These markers are so vibrant. Oh my God, I'm so glad I got them for this. Okay, now explaining vectors in 3D space. So vectors in 3D space are interesting because they're like scientists' way of being like, okay, what exactly is actually happening here? Like, how can we represent what's actually happening with the motion? So let me just draw it out for y'all. So this is the XY plane here, and a vector will always sit on this, well, it doesn't always sit on this plane, but it will be somewhere like in space, so it will be on this plane. And then we're gonna add the z-axis. So this dotted line I drew is, pretend that it's coming out of the page at your face, like towards you. And so that is the z-axis, that's the y-axis, and that's the x-axis. So, when you have the x, y, and z axis, this point here in the middle is called the origin. Now, the origin, it rests at 0, 0, 0. So, this could be represented as 0, 0, 0. Meaning that you don't move on any 3 of the axi. So, if you don't move on the x-axis, 0. You don't move on the y-axis, 0. And you don't move on the z-axis, 0. And so, whenever you're writing a vector, those 3 numbers, you're always going to want to put x, y, z as those 3 values. And so for the origin, it's going to be 0 because you haven't moved. However, let's say I were to pick a point right here. Now, for the purposes of this video, we'll say that it went 2 along the x-axis, and then it went up 4 along the y-axis, and then it went 4 along the z-axis in the plus direction. So if that were to happen, you would denote that as, and let me write it in so we don't forget. I think this is 3, but it would be 2, 4, 3. And for units, we'll use meters. That's our standard unit of measurement. So this would be the vector that you would use to describe that point right there. 2, 4, 3. You went 2 along the x horizontally, 4 along the y vertically, and then 3 outside of the page towards your face. And so yeah, that's how that's going to work. Okay, so another thing about vectors is that you can multiply them by scalars. So what do I mean by that? If you have a number like 3 and you wanted to multiply this vector by that, then you could do 3 times 2, 4, 3 meters. And what you do is you would individually multiply this scalar by those 3 terms. And so you would get 6, 12, and 9 meters as your resultant vector. So those are some examples of things you can do with vectors. So if you wanted to make a vector 3 times the size, it would be, you would just multiply it by 3. And the cool thing about it is you retain the same sort of properties of that vector. Like it's going to be the same proportions, it's going to be the same direction, it's just going to be 3 times the magnitude. Now, when I say magnitude, I do mean something very specific. Okay, so calculating the magnitude of a vector is, the more you do it, it's going to get a lot easier, but so the magnitude of the vector is going to be what happens when you get the square root of the adding up of all the 3 terms. So it'll be x squared plus y squared plus z squared. And then you take the square root of all of that. And that's going to be the magnitude of the force. So what do I mean by that? Okay, so let's say you have a vector that goes two, 2, 2. You're going 2 along the x, 2 along the y, 2 along the z. If you were to try to find the total distance traveled of this vector, which would be the distance from point A to point B, you would complete this calculation here. So you would do f equals the square root of 2 squared plus 2 squared plus 2 squared, which is equal to the square root of 12. And so the square root of 12 is the distance that would be the resultant vector from point A to point B. So what you did was you didn't calculate how long the journey was, because we all know that the journey would have been 2, it would have been 2 plus 2 plus 2 equals 6. So that's separate. That is the total distance traveled. But if you're finding the total distance, the displacement from point A to point B, then you would need to do the magnitude of the equation. And so yeah, that's super helpful, especially on your homework. Okay. Now, why is magnitude useful? Magnitude is useful because a lot of times you'll be given the vector of something, but they won't tell you actually how far away the two objects are, and so you'll kind of be forced to use this equation. And the thing is, you can actually code all this stuff I'm talking about if you don't want to actually like have to do it all by hand. You could code it. It's just something you gotta learn as well on top of the math, but it's totally worth it. Whew, this eraser is, I need to get an eraser. Okay. Okay, so whenever you have a vector, technically you can like change it a little so that it's a scalar. And so that's kind of what I mean when I said the F mag, the magnitude of F, is you're kind of like, it's almost like you're converting the vector into a scalar. You get a number that's 4, 12, 17, and you convert it into something that is just a value without these like brackets here. And it's a good thing to do because when you have a vector quantity like this, there's a few rules that apply that kind of limit what you can do with the vector. So for example, you cannot divide by a vector. So that's something you can't do. There's a few other rules with vectors that you can't do, but that's the main one, is that you can't divide. So if you were to convert this vector into its magnitude, then you could divide it because you wouldn't have to worry about it like being an issue, if that makes sense. So if you were to do 4 squared plus 12 squared plus 17 squared, square root of all that, 16 plus 144, 160 plus 17 squared. So I mean, if you were to take if you were to find out the magnitude of this vector here, it would be the square root of 16 plus 144 plus 289. That's 160 plus 200. Let's see, 160 plus 289, 449. Square root of 449. 21.189. And so this is the same thing as that, except it's not in a vector format. It would be 21.189. And then whatever vector you're doing, so let's say kilometers per hour. So this is an example of how to go from the vector format to the magnitude format. However, there's a caveat. You're going to want to keep track of the unit vector. The unit vector, it's super important, but it's also super simple. Okay, so unit vector. So when you go from the vector to the magnitude like that, you have to make sure that you do the unit vector too, because it's like the only way to switch back. So like when you remember how we just did, like we went from like this to this and it was just like one number? There's a way to bring this number back to the vector, and that's by using a unit vector. A unit vector is it's a type of vector, but it doesn't have a value, or I mean it doesn't have a unit. So now let's do an example with VHAT. So now VHAT is super important because VHAT will allow you to get from the magnitude that we just discovered, force magnitude, and it gives you a quantity with the value, but it's not a vector, right? So there's a way to jump back from this to the vector quantity that we were given, and it's by using a unit vector. So a unit vector is like a vector with a little hat on it. That little hat right there, that means that it's a unit vector. So a unit vector is a vector with the magnitude of 1. So equals, it could be this, it could be this, it could be anything in between those things as well. So as long as whenever you square these values and add them up, and then take the square root of all the adding them up, and it equals 1, then you have a unit vector. So like for example, if you square 1 and then take the square root of it, it equals 1. So that's a unit vector. Let's do an example with something easier. So let's say you have a vector that's 2, 3, 4 newtons. Now this force, the way to calculate the magnitude would be by doing this. So it would be 2 squared plus 3 squared plus 4 squared. Square root of that is equal to 2 squared is 4 plus 3 squared is 9 plus 4 squared is 16 plus 9 is 25 plus 4 is 29. So square root of 29. Square root of 29 is, let's see, 5.38. Double check that. Okay, oh, I was a little off. 5.385. Okay. So that would be the actual magnitude of that vector would be this. Now there's a way to go back to that. You'd multiply it by your unit vector. Now you're like, okay, well how do you find it? Good question. So the way you find the unit vector is by doing this thing goes in the denominator, and then you individually do each of these. So this would be your x value, and that is, let's see, we know this is square root of 29, and so that's 5.385, and this is just 2. So that is 0.371. And that's our x value. Our y value is going to be 3 over 5.385, which is equal to 0.557. And then the last one will be 4 over 5.385, which is equal to 0.743. And that is going to be your unit vector. Now the thing is, this has no units. No units, it's just a number and no units. But when you multiply this by the 5.385 newtons, you'll individually distribute the 5. You'll do this 3 times, and you'll be left with the exact same vector you started with, which is 2, 3, 4. Alright, and so the way to check this to see if it's right is by doing squared plus 0.743 squared, and then taking the square root of all of that should equal 1. So let's go ahead and try that. And it looks like we get 0.9977. And that is definitely close enough to be the answer. So if it's close to 1 like that, that's how you know you got a good unit vector. You just go ahead and check it with this work here. It takes a little bit of extra time, but I'd say it's worth it. So that is how you do unit vectors. And yeah, unit vectors are really useful because, like I said, there's going to be times where you're going to want to go back from this magnitude back to the original vector you got, and having the unit vector is super helpful for that. So always be sure to use your unit vector and calculate your unit vector, even if sometimes you don't have to. It's good to practice. And yeah. Alright, that's everything for today. I appreciate y'all for watching. If y'all enjoyed this video, be sure to subscribe, leave a comment letting me know what y'all like the most, and if y'all want, just let me know what y'all want me to do in the next one. Because I have ideas, but like, I'm open to suggestions, you know? But yeah. Bye!